Hey guys, today we're going to learn about friction. So we're going to look at general facts about all friction, get an idea of what it is. Then we'll talk about a thing called the coefficient of friction, which will help us do the math. Uh, Also, we're going to look deeply at why friction exists. What is the nature of it? What causes it? Because that's illuminating and enlightening when we try to understand the different ways that we use these do the math. Then finally, we'll look at the friction equations. There are two of them, and how we use them. So we'll start off here with general facts about friction. Okay, the first thing is that it is always a force that opposes motion or possible motion, and it's always a reaction force. Now, these two actually go together here. So I have my hands together here, and I try to slide one across the other, I have trouble doing it because there's friction. So the frictional force between my hands is opposing the sliding. However, it's always a reaction force, meaning that there is no friction if I'm not trying to slide my hands. So if I have a pen on my clipboard here, if the clipboard is level, I'll hold it so we can see it in the camera here. If the clipboard is level, there's no friction. But when I tilt it, now there's a gravitational component trying to drag it down the slope, and it's not sliding, so there is friction here. Okay, so if it's not tilted, there's no friction. If it's perfectly level, perfectly flat, no friction. Friction only exists as a reaction force to something trying to drag it down the hill or across the surface. Okay, finally, um, frictional forces depend on the normal force and mu, and we'll get into that in a little more detail in just a moment here. So mu, what is mu? Mu, that's the symbol, it's the Greek letter mu, is the coefficient of friction. And that is a dimensionless number that we use to calculate, that we use it to plug into equations so we can figure out how much friction exists. Now, mu, the value of this symbol here, is determined by experiment, and it's different for every substance and pair of substances. So the friction between my hands can be described as mu. It's the mu for the friction between my hands. But if I put my hand on paper here, well, that's a different pair of substances, so there's going to be a different mu for my hand on paper than there is for my hand on another hand. Okay. Finally, mu comes in two flavors, mu S and mu K, because it turns out that friction comes in two flavors. What do I mean by that? Okay, well, there's two kinds of friction. There's static friction and kinetic friction. And we have a mu for each one of those, which we'll see in a moment. Okay, so why is there friction in the first place? Well, friction exists because surfaces in the real world are rough. They're not perfectly smooth. Even on a atomic scale, if we took a perfect crystal where the atoms are laid out in a perfect grid and we cleaved that plane, so we had a perfectly flat plane of atoms, it would not be perfectly smooth like a pool table or a cookie sheet. It would look more like a box with tennis balls all over the bottom of the box. It's going to be a bumpy surface. So all surfaces at a microscopic scale are bumpy and uneven. So we have a red surface and a black surface here. And when the two objects are just sitting here, those irregularities interlock. The black surface kind of settles down until it's in contact with the red surface. Now, if we try to slide these surfaces past each other, if we try to push the black one to the left, well, the bumps are going to run into other bumps. And we have to push really, really hard until we either break the red bumps off there or the black bumps off, chipping off pieces and smoothing the surface, or raise this thing up, push it hard enough that it gets pushed upwards. And then once it's raised up above, then it can go bumping along and grinding along and slide along. Okay, so static friction is the friction between two objects which are not moving relative to each other. And they're a little bit interlocked. It's hard to get them to break apart. Now, once you get them broken apart and sliding along, then it's easier to keep them bumping along because they never have time to settle back together and interlock again. Okay, so static friction is when there's no relative motion. I can do it on this one here. Static friction is when there's no relative motion between the two surfaces. Kinetic friction is when there is relative motion and the two pieces are actually sliding. And for that reason, we sometimes see this as sliding friction or even sometimes dynamic friction, which means moving. Your book and AP both use this term kinetic friction, meaning that there is motion between them. Okay? Static friction is, well, I'll get to that in a moment. Static friction is the stronger one because we have to break loose of this interlocking or raise the things up, push hard enough to raise the thing up so it can start bumping along the top. So that is stronger. Static friction is stronger than kinetic friction. Kinetic friction is weaker than static friction. Because once we get the surfaces separated and bumping along the surface here, it's easier to keep them going. As soon as the relative motion stops, then they settle back together again, they interlock again, and we have to overcome that static interlock before we can get them moving again. Now, you guys have all experienced this. If you've tried to move furniture, like moving a sofa in the living room for your mom, you've probably said yourself or heard somebody say, once you get it moving, keep it moving, we'll never get it going again. So it's hard to get the sofa broken loose from the rug or from the wood floor. But once it's moving, it's easier, relatively easier to keep it moving. But as soon as you stop, then you have to push really hard to get it going again. Okay, now this means that static friction is a variable force. Okay, it's a variable force because the harder you push, the harder the friction pushes back on you. Remember, all friction is a reactive force. So the static friction only exists if you are trying to make the surfaces slide. So it varies. The harder you push, the harder it pushes back until you reach the threshold where it breaks loose and starts sliding along. And then once you're sliding along, now you have kinetic friction, and kinetic friction is a constant force. It doesn't matter how fast the two objects are moving relative to each other, fast or slow. The kinetic friction, the sliding friction, is always the same, which is a little surprising. But if you do the experiments, you can see that that's actually true. Okay, so this is a summary of static versus kinetic friction. Static friction first. So the equation for static friction looks like this. We do F static. So F is friction, and the type of friction is static friction. I'm sorry, F is force, and the type of force is static friction. And that is going to be less than or equal to mu, which we talked about before. And I'll show you some problems where we use mu, and that'll make a little bit more sense in a moment, times the normal force. Okay, now this is the way it appears in the book. In your AP gouge, they make these absolute values. Okay, so this equation is on your AP gouge. Now, what do we mean by the normal force? Remember, the normal force is a force which acts perpendicular to a surface. So my hand is holding the calculator, and there's a normal force of my hand pushing up on the calculator, which counteracts the weight of the calculator. Now, if I tilt my hand to the side a little bit at an angle, now the normal force is going this way. So to figure out the friction between my hand and the calculator, we need to calculate the component of the weight of the calculator, which is into my hand. We have to calculate the component of weight, which is the normal force. Okay, and that normal force will determine the friction between the calculator and my hand. And as you know, as I get steeper and steeper here, the normal force gets less and less because the weight is acting downward and less of that weight is acting into my hand. And eventually we get so steep that the normal force is not enough to produce enough friction to hold the calculator, and the calculator slides. We'll do the math on this in a moment, but this is the equation for it. Okay, so this is the frictional force, and that is in newtons. This is the coefficient of friction, and for static friction, this is going to be mu s. Okay, and then the normal force is the normal force, and that is also in newtons. Okay, so the coefficient of friction, like I said, it's different for every pair of substances that are in contact. You need to do an experiment to determine what it is. But in your book on page 138, there's a small table with a few coefficient of frictions which come up in your homework problems. Okay, table. Okay. Now, the equation for kinetic friction is very similar. In this one, it is the force of friction kinetic is equal to mu k times the normal force. That's all there is to it. And the same thing. So this is force of friction in newtons. This is on page 138. And this is the normal force also in newtons. Let's run through a couple problems here for it. So let's imagine now that we have a wooden block sitting on a wooden floor, and we are trying to pull the block across the wooden floor. So we're applying a purely horizontal force. And our question is, what is the force to start sliding, and what is the force that we need to keep sliding at a constant speed or constant velocity? Okay, so the equation that we're going to use is this is static friction, and the second one is kinetic friction. So we're going to do friction static equals mu Fn. That's the equation that we're going to use for the first part, for part A. Now, first we have to figure out the normal force. Now we know it's a 5 kilogram block, so we got to figure out the weight of the 5 kilogram block. So W equals mg, that's our weight equation. The weight is equal to 5 kilograms times 9.8 meters per second squared, which comes out to be 4.9 newtons. That is the weight of the block. And since it's a perfectly level floor, that's also the normal force. Also happens to be the normal force. So we're going to look on page 138 to find this coefficient of friction for wood on wood. I want you to do that. I want you to actually get out the book and find it, okay? Because you're going to need to be able to do this, find this table for homework problems. So the coefficient of friction for wood on wood for static friction comes out to be 0.50. Okay, that's what the book uses, so that's what we're going to use. So now we just plug in these values. So the force of friction static is equal to 0.5 times 4.9 newtons. That's the normal force, and we get 4.99 divided by 2 equals 2.45 newtons. Okay, that's our answer. So to break this thing loose and start it sliding across the floor, we have to pull with a force of 2.45 newtons. If we pull with less than 2.45 newtons, then it's not going to move. And the force of friction is going to be equal to the force that we are applying to it. So if we pull with only 2 newtons, the force of friction will be 2 newtons because there's not enough pull to overcome the static friction. So that's that part about the, we have the inequality in the equation that's given. The force of friction is less than or equal to mu times the normal force, right? Once we get up to 2.45 newtons, that's enough. It'll break loose and it'll accelerate. Now, part B, how much force do we need to keep it sliding? For this one, we use the other formula for kinetic friction. FFK is equal to mu K times the normal force. Now, the normal force is still the same, so we can still use 0.5. And when we look on our table on page 138, we see that the coefficient of sliding friction, of kinetic friction, is 0.2. 0.20. So the force of friction is equal to 0.20 times 4.9, and that equals 0.2 times 4.9 equals 0.98 newtons. Okay, so it's hard to get it going, but once you get it going, it's relatively easy to keep it going. Now, there's going to be a period here when we start pulling on this thing, when it breaks loose, when we're still pulling really hard. So during that time, the block is going to be accelerating. It's going to go faster and faster and faster until we reduce the pull to that 0.98 newtons, and then we just keep it going along at constant speed. Okay, all right.